Today, we're diving into a really radical idea from the early days of computing, this massive quest to build a perfectly secure operating system. It's a story all about a technology called the security kernel, and trust me, it might just change how you look at the very device you're watching this on right now.
I mean, that's the billion-dollar question in cybersecurity, isn't it? Can you actually build a digital fortress that is so fundamentally strong it's just unbreakable? Way back in the 1970s, a bunch of pioneers in the field were absolutely convinced the answer was yes. But they knew it meant completely rethinking how you build an OS, right from the ground up.
So to really get what they were thinking, we have to travel back in time to this critical fork in the road for operating systems. After this huge, super complex project called Multics, the whole OS world kind of had to decide what really mattered most.
And this is where you see two totally different paths emerge. On one hand, you've got the approach that gave us systems like Unix. The focus there was all about creating this rich world of features and making everything run as fast as possible. Security was important, sure, but it wasn't the number one thing. And then you have the other path, a much more radical idea. Build the fortress first. This was the security kernel philosophy. The main goal was having mathematical proof that your system was secure, even if that meant giving up a little speed or some fancy features.
Okay, so what is this fortress really? Let's actually break down what a security kernel is all about.
The whole idea was to build this tiny, super minimalist foundation for the operating system. This security kernel would be the one and only part of the entire system that enforces the security rules. The big idea was to make it so small and so simple that you could actually prove with mathematical certainty that it was perfect. Think of it like a central, unbreakable bank vault. Everything else in the system gets built outside its walls. Now, to make this work, the security kernel had to live by three ironclad rules. This whole concept is called the reference monitor. First, it had to be tamper-proof. Absolutely nothing could change its core code. Second, it had to have complete mediation. That means every single request for any file, any device, anything had to go through the kernel for a thumbs up or thumbs down. No shortcuts, no backdoors. But honestly, the third rule is the real game changer: verifiability. The entire point was to keep the amount of code you have to trust, what they call the trusted code base, so incredibly small that you could literally prove with math that it was secure.
And you know, this wasn't just some academic theory. These things were actually built. Let's look at our first case study, a system from Honeywell called Scomp, which took this philosophy and baked it right into the hardware. Scomp's whole approach was pretty straightforward. If you want the absolute best security guarantees, you can't just count on software. You have to design the hardware itself from day one to enforce the rules.
So here was Scomp's secret weapon, something called the Security Protection Module, or SPM. It was basically a special chip that acted as a dedicated security guard for the whole computer. Every single time a program wanted to access memory or a device, it had to get permission from the SPM. And this was just a brilliant move, because it meant all that complex, often buggy code for things like device drivers could run completely outside of the trusted kernel. This kept the kernel itself incredibly tiny, which made it way easier to prove it was secure.
And how well did it work? Well, Scomp was so well designed and so rigorously tested that it literally became the blueprint for the highest possible security rating from the US Department of Defense, the A1 level. It didn't just meet the standard, it pretty much set the standard.
Okay, but custom hardware is super expensive, right? And it locks you into one kind of computer. So what if you tried to build a security kernel for the commercial hardware that everybody else was using? Well, that brings us to our second case study, Ch6.
The big goal for the Ch6 project was to hit that same A1 level of hardcore security, but to do it on standard, off-the-shelf Intel x86 processors. You know, the kind of chips that were starting to take over the market.
But this created a huge trade-off. See, since that commercial hardware didn't have a special security chip like Scomp's SPM, Ch6 had no choice but to run critical stuff like device drivers and the file system inside the security kernel. And that meant every time you wanted to add a new graphics card or a new printer, you had to add its driver to the trusted codebase, making the kernel bigger and making the job of proving it was secure that much harder. And yet, despite this enormous challenge, Ch6 also hit that A1 rating. And incredibly, it's still being used in some high-security systems even today. So when you put them side by side, the whole story becomes crystal clear. Scomp went with expensive, custom hardware just so it could keep its trusted kernel pure and small. Ch6, on the other hand, chose flexible commercial hardware but had to live with the headache of a bigger, more complicated kernel. Two totally different approaches to get to the exact same place, a verifiably secure system.
Okay, so if these systems were so incredibly secure, why aren't we all running SCOMP or Ch6 on our laptops today? Well, that brings us to their very complicated legacy. The reality is, living in a fortress has its downsides. All those rigorous security checks sometimes made things run a little slower. Plus, they weren't compatible with all the software that was already out there, so everything would have needed expensive rewrites. At the end of the day, the market voted with its feet. People wanted the massive, feature-packed worlds that systems like Windows and Unix were offering, even if that meant accepting a different and maybe even greater kind of security risk.
But here's the kicker. The story doesn't just end there. The ideas from these security kernels, they didn't really die. They were just way ahead of their time. Take a look at any modern computer processor today. It has a feature called an IOMMU. It's basically a hardware security guard that stops any device you plug in from messing with the main memory. Sound familiar? It should. That is exactly the problem SCOM's SPM was built to solve over 40 years ago. The ideas from that old fortress are now standard features in our modern digital world.
And that brings us right back to where we started. We live in a world of non-stop data breaches and sophisticated hacks, and a lot of them exploit the very complexity that won the market all those decades ago. It really makes you wonder, doesn't it? With the powerful hardware and new tools we have today, maybe it's time to take another look at the fortress. Perhaps that path not taken still has a few lessons left to teach us.